this webinar on unlocking demand-side flexibility services. The focus is on creating business value from energy flexibility with experiences from the Resonance project and examples from pilot sites in Greece and Sweden. My name is Louise Riley, and I'm here together with our three speakers, Mariza Tzouvali from Athens University of Economics and Business, Peter Rosengren from CheckWatt in Sweden, and Per Salomonsson from Mölndal Energi, also from Sweden. Moving to the agenda, if I may. Yeah. So first, Mariza will introduce Resonance and its pilots with focus on the business use cases and zooming in on the Greek pilot site in particular, which has district heating optimization at its core. Then Mariza is followed by Per and Peter, who will give us insight into the Swedish pilot site and how energy flexibility is utilized from household batteries and in the smart planning of heat and power production. After the presentations, we'll have a Q&A session, so we invite you to ask questions using the question option in the toolbar. Now Mariza will introduce us to Resonance and the business use cases with focus on the Greek pilot site. Thank you.
Okay, hello. I am Mariza Tzouvali from STEcon Group of Athens University of Economics and Business. First, I will be presenting, saying a few things about Resonance in general. I'm not sure if okay. So what is the problem we're trying to solve here with this Resonance project? Buildings consume 43% of Europe's final energy, and heating accounts for almost 80% of the residential energy use. Now we have more electric vehicles, electrified heating that introduce new flexibility potential in this space. However, this demand-side flexibility is still costly and fragmented, mainly due to interoperability gaps, heterogeneous devices, and the lack of scalable business models. So Resonance tries to address these barriers with a standard-aligned, cross-sector, and plug-and-play framework. And now let's take a look at this framework. We have three catalogs of microservices. The resource manager services at the lower level, then the SEM catalog, the customer energy manager services, and at last the aggregation catalog for the flexibility and market integration. We introduce a narrow-waist interoperability model aligned with European standards, and all these microservices are packed into a data and service marketplace that enable this scalable deployment. I apologize, I don't seem to have control. Okay, maybe now. Okay, now let's take a look into the pilot sites that were tested during Resonance. We had 6 different countries with different aspects that were studied. For example, in Finland, we had hybrid heating optimization and explicit DR. France had smart TV charging in a pilot site with charging points and photovoltaics. Germany mainly focused on industrial and residential self-consumption under DSO export limits. In Greece, we focused on district heating optimization, employing implicit and explicit DR, and cross-sector heat and electricity integration. For Slovenia, the pilots had a main focus as residential prosumers with PV, batteries, and sometimes EVs. And then in Sweden, it's the combined heat and power utility plant optimization using the thermal inertia and multi-vector flexibility. The economic impact and the benefits of Resonance are multiple for multiple actors. So if we take a look at the building owners and the prosumers, for them, new lower energy costs are unlocked through smarter consumption and smarter self-consumption, and the access to new flexibility programs. For the ESCOs and other software solution providers, there are new service offerings that are enabled by these CM, RM catalogs and this service marketplace. Additionally, they can have reduced integration and complexity thanks to these standardized interfaces. Aggregators and retailers can have more accurate flexibility forecasts, automated bidding, and more reliable flexibility portfolios. District heating operators can optimize their heat production and act as flexibility providers. And on a system level impact, we could see higher RES integration, reduced peak loads, and generally a replicable and iterable model for Europe's energy transition. And now I will move on to the Greek pilot case and talk a bit more about what we did in this pilot. Specifically, the main goals were to show how a district heating operator can become an active flexibility actor using resonance tools to unlock new revenue streams, reduce operational costs, engage end users in flexibility, and test real DR events with households and public sector buildings. The overview of the pilot, we had a cross-sector energy flexibility across district heating and electricity in Ptolemaiда. It is unique because the district heating operator acts both as a heat producer and an aggregator. At the pilot site, we had 45 residential buildings and 3 municipal buildings participating. And from the district heating operator side, there was electric boilers and the tap geothermal hot water used, while on the consumer side, we had district heating and heat pump flexibility. We tested 2 DR models, explicit and implicit. And we'll start our analysis with the explicit DR events. Generally, explicit DR involves direct payments or incentives for the participants to modify their energy consumption based on specific or direct signals from a producer or TSO. Specifically in the Greek pilot, we had the DHO who uses electro boilers. So a load reduction directly reduces the electrical consumption of the DHO. The users would receive personalized thermostat adjustments and rewards points via the SEM app that was produced during Resonance. And all these actions were derived by the Resonance convex optimization module in the aggregation platform. Also, there were simulated bids for the flexibility market, but of course, this was only in simulation mode and not in actual participation. The outcome of the pilot results was that we had an average flexibility of 60.5 kilowatt hours per event. We achieved the target in around half of the events that were tested. And from these pilot results, we computed a net margin profit for the aggregator at almost 30 euros. However, it's important to look at it at the larger scale and see how this model could work outside the pilot, but in real-world operations. And for that, we did this like business model and economic analysis. We made some assumptions. Now we amplify the consumer base that is responsive and flexibility providers, and we assume only 10% of the district heating operators clientele subscribing to such events, which is around 2,000 users. We assume similar flexibility gains, and of course we have to assume some additional costs for the DHO because they will have to pay some license fees for acquiring this aggregation platform, probably some hosting fees for hosting it, and also some additional personnel for running the aggregation platform and also support the customers. The possible outcomes from this analysis came very successful and achieve an IRR of 80 to 90% and a ROI of 2%, while the end users can unlock new revenue streams, resulting in a moderate 1 to 4% of cost savings. In the next slide, we can see the cash flow of the DHO in the baseline case, which is the red one, versus the explicit DR case, where in the simulations, we tested one scenario where it's just load shifting, and then the other scenario, it's that the users respond to explicit DR by completely reducing their demand, which is a bit more attractive for the DHO. However, both appear to have benefits compared to the baseline case. And now, sorry, we can move on to the implicit DR events. Here, we rely on customers to adjust their consumption in response to price signals. And the Greek pilot, we have this combination of tap hot water and electro boilers that are used for the heat production. And the dynamic prices reflect the switching between the sources. The resonance optimization engine calculated the least cost combination of heat sources and generated the corresponding dynamic pricing signals that were delivered to the end users. The SEM app displayed these hourly heating prices, and users received the cost-saving recommendations. So in the pilot sites, we observed clear load shifting behavior from the users due to these messages. But again, it's important to see how this could scale in real-world environments. And so when we did some simulations for the economic analysis and expanding this beyond the pilot, again, we followed similar assumptions, like the fact that we have 10% of the active DHO clienteles to respond to this dynamic pricing. Again, it's around 2,000 users. We have similar load shifting behavior per user, and of course, these additional costs of licensing of the solution, hosting it, and the additional personnel that is needed for this. And this results in very high IRR of 790% and a ROI of 24%, while the users enjoy 6% savings. So this is, of course, a very high number, and we can also see it in the results of the cash flows that are projected against the baseline. And here, the biggest impact is not really the implicit DR part as much as the fact that the DHO optimizes its heat production. So with resonance, the DHO can continuously evaluate tap hot water availability and electro boiler costs, forecast the demand, the weather, and the electricity prices, and select the least cost combination of the heat sources. So then they can reduce the reliance on high-cost electro boilers during peak electricity hours, smooth demand energy peaks, and stabilize this network operation. So this is where the true economic potential lies, and this is why the results in this simulation are so positive. So to sum up the results, the resonance implementations in the Greek pilot show that demand-side flexibility is not theoretical, but can be practically achievable. The district heating operators can become active flexibility actors, unlocking new value streams. The end users can participate meaningfully by means of intuitive tools and personalized guidance. As for the cross-sector optimization, it can deliver real operational and economic gains. And the explicit and implicit DR event planning can be adopted with minimal additional cost. The resonance framework provides ready-to-use SEM, RM, and aggregation modules, and the business models that were examined show strong long-term sustainability. And I think this is all from my side.
Thank you very much, Mariza. Very interesting. And now we'll give the floor to Per, talking about the Swedish pilot site and how flexibility has been utilized through batteries and smart heat and power production planning. Okay, Per.
Thank you. We will make a joint presentation, but I will start here and showing the Swedish pilot that comprises actually two parts, and one is consumers with a battery and photovoltaics, and then the second part B is about district heating customers. And the thing is, in the district heating system, we have this combined heat and power plant that produces both heat and electricity. So there we have a cross-sector flexibility, and also a part of our customers in the B2 part of them, they have both district heating and heat pumps. So also there's a flexibility to choose between the way to heat up the buildings. And to give an overview of the size, we have this pilot A with the batteries. There's around 190 houses with batteries, and the district heating part B, we have again two subparts. One where we talk about the inertia, heat inertia. There's 12 big buildings, 1,500 apartments, and for the B2 part where we have district heating and heat pumps, there are they can switch then the heating between district heating and heat pumps. So there's around 0.6 megawatt electric and 2 megawatt heat in that pilot. But first, Peter will start talking about pilot A with the houses with batteries. So over to you, Peter.
Thank you, Per. So my name is Peter Rosengren, and I am the R&D director of CheckWatt. And CheckWatt is an aggregator in Sweden that provides virtual power plant services. And it doesn't move. And we have been responsible together with Mölndal for the pilot A, where the focus has been on prosumers and the flexibility they can provide is from mainly batteries, but also PVs, and in some cases also EV chargers. These units are controlled by an existing energy management system installed at our customer sites, and we have extended that in the project with new intelligence and with new resource managers, as Maria explained. So a resource manager is basically, in our case, like an adaptation for a certain battery type. And the focus is here on using the Resonance Customer Energy Manager to develop different services that will optimize the value for our resource owners. They are by combining FCRD, which is on so-called ancillary services, which is being procured by the grid owner in Sweden, and that is to stabilize the grid. And that service, we are extending what the resource owner can do. For instance, increasing the self-consumption. So when you have solar installations, you will, if you produce like a surplus, you can either sell it to the grid, or you can store it in a battery and then consume it later. If you consume it later, it's more beneficial because you save more money since you save on the energy tax. The other option is to do what is called energy arbitrage. That means that you can charge or buy electricity when it's cheap, normally during nighttime, and then you can sell it back when the price is high, which often occurs during the evening, for instance. That is two ways of increasing the value for the resource owners. Another thing we have been working on in this project is to make it possible to use the battery on different flexibility markets, not only the FCRD, but also use it on what is called the local flex markets. In our specific case, this market is Effekthandel West. And by the fourth thing is that while we are combining all these three things into optimizing through a multi-service stacking thing where we are using all these together to really maximize the value. And the third important thing is to make this very seamless for the customer so that it is included into the normal electricity bills. So we have worked on integrating the invoicing of this with the existing. Sorry, I'm trying to move here. Yeah, okay. So this is how it. By the way, to the left there is a typical installation, how it looks like in our customer or the pilot user site, where there is a battery at the bottom on the floor, typically in a garage, and there you have also the PV inverter. And the income or revenues generated from the services is then included on the normal bill from Mölndal Energi, so that the revenues are simply deducted from the cost of electricity. Sorry, move too fast. So on one of the results we have achieved is working with what is called the automated consumer flexibility manager of resonance, in order to improve, how the optimizing the battery control. And this is optimizing on the spot price. And if you see here, you can see how the yellow line down here is the spot price, and the red lines here is the electricity consumption, and this line shows how the battery is actually charged when the price is low, and then the optimizer discharges the battery when the price is high, so that we make a little more money, and then it also charges again when the price is at the bottom, and it discharges when the price is really high. So this was a good day. And we have to keep that or we are keeping that in the limits of what is allowed from the FCRD point of view. There are these services that the grid owner procures, there are a lot of regulations around that. So the battery cannot go below 30% charge level or above 70% charge level. But this is what this the optimizer does. And you can see also a nice effect is also down here. You can see that it reduces some of the power peaks. And at this time, we still had power tariffs in Sweden, so it was a good thing. Now there has been a decision to postpone these tariffs, but it will eventually be coming again, and it's a good way if you can cut down the peaks for the users. And this shows how this from the normal now compared with the diagram in the beginning, you not only have now revenues from the FCRD service, but you also have additional cost savings, the green parts of the bars here. So that shows how the user has made a little bit more money out of this. And going to the second thing here about the multi-market, how one can utilize the flexibility resource on different markets. So the local capacity market, which is being called Effekthandel West. So basically, one could say that there are two types of flexibility markets. One which are procured by the grid owner, like FCRD or FCRN, etc. These are requested services in order to balance the grid in case of, they are based on unforeseen deviations. That's when these services will trigger in, like an insurance. The local flex markets are more local to a DSO like Mölndal, And the problem here is that people tend to do the same thing at the same time. Like everyone is having a shower in the morning, and that causes the hot water boiler to start, or everyone is cooking food in the evening, which causes the ovens to start, and that creates peaks in the electricity consumption, and that is handled by buying flexibility. The DSO can also level that out and minimize their own cost, and also pay the user some money for that. And this market, we were working on that, and that was part of. So we started already in the beginning of the project in 2023 season, 2023-24, where we just a few bids, and then there was a full-scale bidding in 2024-25. That was in the second year of the project. However, there was a rather mild winter. So the real effect we saw in this year, where we were operating from November or beginning of December until end of March. You can see first here is the area where we were, where the local flex market is available, and this shows the bidding interface from how we can put in bids to the local flex market. And this shows now there is an additional color in the diagram. We can also see now the blue ones. That is how much the user here made in terms of the local flex income. So now it is the yellow one was income from the grid services, the green one from savings, and the blue ones from local flex market. So it proved to be a very, very beneficial thing for the user. And I think I will thank you. Sorry. That's for part B, pilot A. Now over to pilot B.
Okay, thank you, Peter. And now, well, Peter has told you about the batteries. We also had a part where we used the district heating and combined heat and power production. And where does the value come from here? Well, first of all, there's two types of building flexibility. One is using, which gives us a possibility to shift the heating demand in short. And then we have the customers that have both district heating and local heat pumps, and then and vice versa. Where does the value come from then that we are targeting? Well, one is when we can, in a combined heat and power plant, it's important to actually match the heat and electricity demand with the markets, and with the also when you produce electricity, you also produce heat, and you want to actually optimize that. Then the spot price in electricity varies over the day, and that's then we want to sell as much when it's high prices for the production, and the users, of course, they want to use as shift them to use more electricity when it's low price. In the Mölndal case, our district to our neighbor Gothenburg, so we have actually a mutual planning there where we exchange heating, and then we have set prices for that. So that's another thing that we can earn money or excess capacity to our neighboring network. And then we have this local flexibility market, as Peter told you, where the local DSO, which is our net company, then is buying flexibility from the consumers in the local grid, and that gives them the possibility for users with heat pumps to switch off the heat pump and get paid for that, and then use district heating during this time to provide the necessary heat. And this the general value in this system then is then shared with the customers or the consumers. And what do we need to be able to do this? We have we need to actually base this on a hourly marginal cost for the district heating. So there's a value actually shifting the heat production to the hours when it's beneficial to use heat and move it away from expensive hours. And then what we also do then is this flex market has an hourly bidding, and then we include that remuneration in the calculation in the price for the customers, so that makes the actually the district heating very cheap for these hours, so very beneficial to use the heat district heating in those hours. It also is necessary to have this CM system where with a model predictive control and indoor temperature metering in the buildings to be able to actually calculate the available flex and how much we can take out of the buildings or charge the buildings, and how much to do that. And then for the resonance platform, there's an integration between the CEMs that control the buildings, an aggregation platform, and then a coupling to the product optimization and the actual SCADA system that is actually running the combined heat and power plant. Okay, so the beauty of this building flexibility as a service is that we create value for the whole energy system, which becomes more efficient. We can reduce peak loads and congestions, and we utilize the system better. For the end customers, they get a lower cost, and the system is automated to a very high degree, so they don't have to do any active choices. And for the energy company, we get an optimized production, and we get increased income from electricity and from heat. And we also will solve our power problem in this local flexibility market. And last but not least, we get a much better and engagement with customers. One is that we share our value with them. Another thing also that we get, we can see if the building is working well or not, and we can tell them it seems that you have some problems with your heating system, and you maybe should try to fix that. So this is then the system where we have, with a lot of benefits for all the actors. Okay, sorry. The thermal inertia. You can see pictures. There's actually 9 buildings with around 1,000 apartments, 2,000 residents approximately. The other is a little bit smaller. It's 3 with around 400 apartments and around 800 residents. And we managed for the last heating season here, we had actually the system running for a full season. And here you can see how the heat demand varies over the season. It's the blue curve. And the orange curve, you can see actually where we request flexibility and how much flexibility that is actually provided. So you can see in this range, there's around like 300 kilowatts charge and discharge power, and the maximum heat demand was around in this part of the pilot. We run for during these hours. We had active control in 1,100 hours. We requested around 500 megawatt heats, and we actually got half of that, and in this part, this was a problem a little bit in the spring when the weather got warmer. The buildings were actually hotter than the control temperature, which means that we had a problem to actually control the flexibility as well as we had hoped. But what we did here, actually, we connected this flexibility to our production plant in during the full season. So the actual operation of the CHP plant was the reference case. But what we did that for each day, we actually made a re-optimization, but included the flexibility in this pilot. So then we could, okay, we got a signal, and then we could send that flex request to the buildings, and we could see and run and see how they responded. So, and then we could also calculate how much value that flex would be. So we were not actually running the CHP plant with flexibility, but we took the actual operational plant and see how much could we gain in that case with the flexibility. This is was, we think, a very interesting thing to do. However, I mean, we only, in this way, we can only get some of the value streams included, because, for example, for the ancillary services, that requires that we would have to adjust our bidding strategy, and that was not done. So the value that we calculated in this case is a true value, but it's not the full value. And actually, the most of the value was that we could actually increase the amount of electricity sold when we had a high electricity prices. And you can see how this the amount of charge and discharge energy varies over the season from November to May. And you can also see, maybe even more interesting, that the amount of flexible energy varies over the season. These are the blue ones. But also the actual value of the flex varies. So, for example, if you look on December here, you can see that we flexed quite a lot of energy, but the value for the flex was around 10 euros per megawatt hour, while in January there were less hours and less flexibility requested, but we reached a value of around 25 euros per megawatt hour for that flexibility. This shows to us that there's a lot of optimization to be done, and the value that we can get out of this can be higher than what we actually got in this. And to conclude this, and to leave some time for questions, I mean, as I said, we calculated value, which is system will be even higher, because we can then include even more value streams. However, it's so that in our energy system, which is quite, I would say, be the driver in many cases for flexibility. Our value of flexibility is still relatively low per building, and then so we need to do some value stacking here also to actually get a good business case. But the thing is, I mean, this advanced building control is a requirement to make this work, and the CM system, it generates customer energy savings. So they actually can pay a little bit for the installation and still get a really good business case, because they save energy because of this model predictive control. And as I showed, for example, we can see, what we often see is that even if you think you have a very good control of your building, very often you have a little bit too high temperature, and just that insight would save you several percent of your heating demand. So what we do in our is to create an overall positive business case by customer energy manager for the customer, and then we add our flexibility on top of that, because the additional cost to integrate flex in the overall system is quite low, and it generates a net value that we share then with. So this is why we are doing this, and this we think is, as I have shown to you earlier, to the benefit for the system, for the customers, and for us. I haven't talked so much about, because of the time limits, about the second part where we have these customers that switch between heat pumps and district heating, but that has also been a very successful part of this resonance project. The only limit is that there's not so many customers that have both district heating and local heat pumps, but we have demonstrated here that this is a really good case for both of us, and in particular it gives a very good contribution to the local flexibility market. So this can actually really contribute to solving the restrictions or the what's called limitations of the when there are peak power in the electricity grid. Another learning, I would say, that is to actually get the most out of the flexibility, you still need to have well-adjusted heating systems. As I showed, if a building is not well adjusted, you can't just put on a CM and think that everything will work. I mean, if you have a heating curve that is way off, you need to adjust that heat curve first and then run your flexibility. But once you do that, you can get a really good case both for the customer and for the district heating company, and also produce some more electricity on the way. Okay, thank you. That concludes our presentation.
Thank you very much, Per and Peter. We now move to the Q&A. So let me see if there are any questions from our audience. There's one. So this is for CheckWatt. So you, Peter, as an aggregator, what is the main value of resonance in relation to your service and your business model and customers? So what's the main added value of resonance you've been able to provide? So Peter, are you there?
Sorry. Yes, I'm here.
Good.
I was speaking.
Yes, I guess so.
Yeah, okay. Yeah, it is the optimization possibilities offered, and there are directly to the customers that we can offer more services, and then the combination of services and savings. That is one thing. Then there is, of course, some stuff underneath also in terms of the standard protocols being used and stuff like that. So, but that is one thing, and the possibility to actually be on both the FCR D market and the local flex market in the Gothenburg area, which we are also now able to replicate to other. There are some other local flex markets being popping up in Sweden, not as many as we had anticipated, but so the development is slow, but it is moving, and I think that was one of the main thing here, that we did get the experience from being able to generate revenues from two different markets.
Okay. So talking about the future, and this could be for both of you, how will you continue to work with energy flexibility as part of your portfolio and business? If we start with Per, how are you going to work with energy flexibility and optimization in the future?
Well, we will continue I think we are quite happy what we have achieved, but we have still only connected a very small part of the building. So now, I mean, the challenge is to actually connect more buildings so that we get a really workable, because still this pilot is still a very small part of the actual heat, and we need more to actually to do something that is really powerful. We need to connect more buildings. So that's but I mean the principles and the thing to connect and aggregate different systems the way we've done, we think is a way forward. Continue.
Yes. Okay. And Peter?
I would say that I would differentiate, or from our point of view, we can differentiate between two different flex markets. One is a TSO market, and that is a quite mature market, and the TSOs are in most European countries is very far here and mature in procuring services here. So in that sense we will simply expand what we are doing to different European countries. The other market is the DSO market and the local flex markets, which we are really happy to have worked with. I would say one of the DSOs that are in the forefront here of local flex, because this is, and that is not only in Sweden, it's also all over Europe, that the DSO buy or procurement of flexibility is much less developed in most European countries. So there it will be more still more of pilot testing, I would say, and stuff like that.
Okay, thank you, Peter.
I can add to that. Actually, I think that part we are very happy with the collaboration in Mölndal together with CheckWatt, which is one part of the resources that we can use, but it is still we see this as an important part of how to manage, which is a growing city with see this local flex market as a really important thing to continue to work with.
Good. And Mariza, now you're here as well. What about in the Greek case? How do you see energy flexibility in the energy stream there? Obviously, you've had one city to focus on, an area, but how do you see the future there?
Yeah, so I mean, for Greece, we have to take into consideration how the regulatory framework is not really there yet. So we have a lot of steps ahead. We are paving the way in order to be ready when this flexibility market can be actually implemented. From our side, we are a research group and from university. So our goal is to provide like these solutions and make evident how we can actually transition. As you said, now we tested it on the district heating operator of Ptolemaida, just one city. And maybe we can view how this can be expanded to other cities and showcase how flexibility can actually be implemented within the Greek smart grid.
Okay, yeah. So some challenges ahead, especially also considering the need for new infrastructure, updated infrastructure versus energy flexibility, and how that dynamic will take place. If we move to the last slide, I would like to thank our speakers and online participants for joining us at this webinar. You can revisit it through our project website just immediately after this has taken place. So we'll upload it to our website so you can revisit parts of it. You can also find other webinars that highlight key results from resonance, from standardization to modeling control. And with these words, I would like to say thank you and have a nice day.